To begin, the wood of the day. We're back to hardwood, although this is a pretty soft hardwood. Not as hard as oak or hickory, but a very nice wood, one of my favorites. The state tree of Tennessee. I used to live down there for quite a while. This is yellow poplar. Here, I'll start it again. And yellow poplar, as you can see on the screen here, has these beautiful little flowers. It's also called a tulip tree or tulip poplar. It has a very smooth grain. It's pretty rapid growth, and is used quite a bit commercially in the South. Not so much for construction, but a lot for furniture. Let's see what they say here. Furniture, interior molding, siding, cabinets, musical instruments, amazingly, not sure what, and structural components, boxes, pallets, crates, so that'd be a waste. Also, they say it can be made into plywood, but I don't think I've ever seen that. More often, furniture and in construction as trim work, and it is used for trim because you can work it fairly well. You know, like on a what do you call those things? A router, or it's being smooth grain. It works pretty well, shapes well. It has a beautiful kind of green color. Sometimes when you get boards of it, you'll get these actually dark purple streaks through it, which is amazing. So it varies from a white to, I guess the core of it's more green, and then it gets these purple streaks through it. It is cut quite a bit into boards in the where it gets used in furniture and other things, but you can readily find it even up here. I've seen it at Lowe's or places. It's pretty available. Like I say, in the South, it is commercially grown because it grows fairly rapidly. I know when we were down in Tennessee, the university forestry department was working on a project to try to breed it, or cross-pollinate it, whatever you do to trees, to get a rapidly growing, stronger and straight variety. It was based on the tulip poplar, and they'd grow that then commercially. The goal was, like in 10-20 years, you'd have it ready to harvest. Anyway, so that's tulip poplar. Let's see, I think we have a couple more pictures of it here. Let's see what we got. I have no idea what that is. Okay, here's the area which it grows in. Look at that, includes southern Michigan. In fact, I know there's one just down the street on Glacier. Where that big, what do you call it, graveyard is. There's one at the edge of the graveyard, because I walk past that sometimes going to the parking lot. And in the spring, like I say, it gets these beautiful tulip-shaped flowers that are orange and white, kind of an orange and white. Let's see if they've got a picture of one. No, sorry, I don't have a picture of one. There's the heartwood is more green, like you can see in that picture. Okay, so that gives you an idea of tulip poplar. Let me see, I guess we can close this guy. Okay, there I go. And now, the topic for today is kind of a fun lecture. This is, here we go. Right here is, you can see yourself, tulip poplar. Still talking about columns. what I kind of like to do is draw a comparison between the different ways that you can structure a column. Obviously, you know, the simplest things like we were talking about the studs, or a solid column out of dimension lumber. But you could also nail those together. You could just put them side by side. That's this option. You could use that larger dimension and make them solid. They could be, to the point of being timbers, or just a little bit bigger. If I double this, this is 2 by 8, I believe. I'd have a 4 by 8, right? Or you can go to the glue lam to get larger sizes, or there's some methods to combine them, which increases their strength a little bit by nailing them together or bolting them together. And then the last thing we'll look at is this connected with split ring connectors. Okay, so let's see here. Type 1. So the first one we said would just be if and would not, this will prove to be probably the least desirable of the options. So why you'd probably not do this is simply put them side by side. If I'm, and I'll try to do this consistently with the size. I'll try and consistently use the same size and material as best I can, wood, for all the different options. So first option, just put 2 next to each other. Don't attach them, just, and actually that does happen, right? Particularly in stud walls, you double members sometimes. And you can double them without bothering to nail them together. Just put them 2 together. Okay, that does double their strength, but not much beyond that. So the procedure in determining the capacity is what we've done already. You have to check that, where's my little marker? You have to check this LE over D ratio, make sure it's under 50, put the adjustment factors on it. The critical one, of course, is CP, the buckling factor. Calculate that, and then you can get the allowable stress, and with that, the capacity. If you essentially set the allowable stress equal to the actual stress, and then calculate the capacity. Okay, so for our little column that we're going to do, if I do this with, these are 2 by 8s, right? If I use a 2 by 8 here, which is, I believe, what I've got here, although maybe I got a 2 by 10. I should have brought something. I don't have anything to measure it with. What do you think? 8 or 10? Huh?
You can measure it.
You can? How? Oh, I gotta see this. How can you measure it? You've got an app for it. Okay. All right, so this is, in fact, a 2 by 8. I kind of thought it was. All right, a 2 by 8. So we're just going to put 2 of these together. Well, of course, the limitation on a single 2 by anything is that LE over D can't exceed 50. So keeping that, where'd my pen go? Trying to keep that under 50 limits my height. So I'm going to do this example with a kind of ridiculously short column, but it's the only way I can include this one in the comparison. So we'll say the column's 6 feet high. Okay, it may be just a compression member somewhere, but it's 6 feet high, 6 feet long. And when I calculate then for the actual dimensions of the 2 by 8, I'll come up with a slenderness ratio in the y direction. This is, they call it 1 and 2, but I get them mixed up. Of 48. Okay, so that's less than 50, but obviously with a slenderness that high, you're not going to have a very high CP. CP is going to be pretty low, right? Because remember, you can always think of your CP graph, right? It's the same as the Euler curve. And if this is 50, 48 is right next to it. So this is probably, I don't know, it can't be any more than 0.1. It's probably less than 0.1 down there at the bottom. Okay, but that'll be that. It'll at least be double. We'll use two of them. The CD, we're going, I think this is based on the roof live load. Okay, so for the roof live load, we've got 1.25. And then CF, you'd have to look up in the little table, right? And I might even have that. No, it doesn't look like I have it on the next slide. But that would be 1.05. Okay, so then we've got to calculate CP. So we put those other two factors on this is the value for hem fur. Oh, this is even a piece of hem fur. That's why I brought that up here. For hem fur number 2, we pull these values out of the NDS, right? And we get a CP. Oh, wow. Yeah. CP is pretty low. 0.09. So you've lost, what is that, 91% of your strength is gone because it's so slender. Okay, so that's already a disadvantage of trying to do it like this. But on the other hand, it's double the strength of one of them. If I only had one, this would end up being, I am doubling the area, right? So there we go. We double the area. So it does double the strength of a single one, putting them together. Okay, so we put those CP factor on there, calculate F prime C, and we'll come out with a total strength. So it might be fun to try to keep track of these. This one is the option 1, right? Dimension lumber, not nailed. And we can, let's see, maybe we'll keep track of the CPs. Is 0.09, and the total strength is 3,000. Yeah, it sounds not too bad. 3,051,571. So 571. Okay, 3,571 pounds. Okay, so that's for that option. That'll be kind of our base, right? Now, if I rather than using two of them, I had two 2x8s, right? I could just use a 4x8, and that would still be dimension lumber. This would have been, maybe I should have said, 2 2x8s, and then we'll say option 2 is a 4x8, right? Okay, so that'll be that. Okay, now when we calculate the slenderness, it should be a little bit better because I've got to double the thickness of it. So otherwise, the procedure is exactly the same. The properties I'm using are exactly the same. I'm just changing that. And here, I'm sticking with a real piece. So really, it a little bit more than doubles it, right? If I just doubled a 1x, I'd only be coming up with 3 inches. So going to a 4x, you actually pick up a little bit of area, right? You're getting a 3.5 width, actually. So the area is a little bit more than we had for doubling the other one. Slenderness ratio looks a lot better. Oh my goodness, now we're in that middle range almost. If this is 50, 20, oh gosh, yeah, I should be, 20, yeah, I'd be higher than 20. 25 would be the middle. so I should be higher. So I might even be a little bit above 0.5, right? I would hope. So it should be better. We've got these turn out to be the same, even, I think that one was even the same if we look it up, for compression. Whoops. For compression, you have to make sure you get the right column in that table. Okay, so then we go ahead and calculate CP. Oh, somehow it was a little bit under 0.5, but it was close. It was close to 0.5 at any rate. Yeah, and so we put that one in there, and we come out with 781 psi. The area is a little bit larger, so wow, the total looks a lot better. Now we've got 819. Okay, whoops. So this is, CP was, what do we have?
457.
457. And the load is 19,819. Okay, so that one's, so we go from 3,000 to 19,000. What a jump, just from making it solid, right? So there'd be a big advantage to using a 4-by rather than two bys, for sure, for that reason. Okay, next we'll look at the glulam, and we've not really talked about glulam. We're going to get into glulam next week in more detail, but we can look at the column design. Is not much different from solid lumber, except we're using a little bit different tables. So this was at the project in Vancouver, the Brock Commons. I don't know, did we talk about that? Did I show you that video? I don't think so yet. Maybe next week we'll take a little bit more detailed look at Brock Commons. Was an example of a one of the first on this continent, the first, because it's up in Canada, the first real tall wood structure. The wood structures hadn't been used at much height because of fire considerations. They're worried they'd burn, right? But as you get into this mass timber, I mean, that would be true of dimension lumber. It's thin enough that it would burn pretty rapidly. It's like a bunch of matchsticks. But the heavier timber, the glulam and the CLT, is thick enough that it doesn't burn so rapidly. So there's a certain fire resistance just in the thickness, like an hour per inch, I think, is what they usually calculate. So now they've rewritten the codes recently to allow these, and we're starting to see them in the U.S. There's one down in, is it Atlanta? I know they're building one up in Milwaukee that's like taller than Brock Commons, which is...
How tall is it?
This is 18 stories, Brock Commons. I think the one they're doing up in Milwaukee is 20-something stories. So they're getting pretty tall. You can, according to the IBC, I think you can go, I forget. I probably shouldn't say from memory, but it's over 100 feet unprotected, totally unprotected, like in this photo shows, unprotected. It's just exposed. And that has a certain advantage in just the architectural aesthetic of it, right? The wood looks beautiful exposed like that. You can imagine it would be much nicer than a concrete room, walls and columns, to have this wood.
And also, do you still use 2 concrete floors at the base?
Yeah, down at the base they do have concrete floors. And that has more to do with the structure and there's a parking garage down there. And for the parking garage, they had to, and so most of them end up with a parking garage at the base. I think the one in Milwaukee also has, like, the first 4 stories are concrete, but it's a parking garage, and then it switches to wood on top of that. And in this Brock Commons, the lateral stability comes from elevator towers, which are all concrete. So in that example, that's mixed, lateral stability is coming from the concrete. But you wouldn't have to. There's some, I think, that have been designed totally with wood without. There are a couple in Rome, I know, that are pretty tall. I forget how they were done earlier. Anyway, but we'll talk more about the CLT and the glue lam next week. But this gives you, this is kind of an idea what it's about. And you can see here the procedure is very, very similar. One difference is instead of CF, they use a factor called CV. It's a volume factor. For the dimension lumber, CF was a size factor, right? And it's basically, it is a volume factor, really. I mean, it's basically looking at the volume of it. But it's a little bit different factor. It doesn't take into account the length. That's right. So it's not really the volume. It's just the area. It'd be like CF is you could almost call it an area factor. It's a size factor. But CV does include the length of it in the factor. And so it really is the full volume. However, for columns, you don't use it. So that one gets left out. Otherwise, you've got these factors. CP is also in there. And when you calculate CP, you remember there's a constant C that goes in the denominator, and that for glue lam is different. It's 0.9. I think we'd use 0.8 for the other ones. So we calculate the size here that we could use is exactly the same as the 4x8 dimensions. I think the 8 is 2.5, isn't it? 7.25, and this is 7.5. At any rate, okay, a little bit different, but this is a standard size for glue lam. And it has then a slenderness of 20.5. I guess that comes out to the same as the solid lumber. I tried to pick a grade that was pretty close. This is a glue lam grade. So I think the other one was 1300. This is 1350. So it's pretty close. It's I think a visual grade 2, I think is what they call it. And the E-min, I think, is a little bit higher. But those are the numbers out of the, in fact, I can show you where they come from. They come out of the back. If you go all the way to the back of the NDS, interestingly enough, the tables suddenly turn landscape, and all these landscape tables are glue lam. So it makes it a little bit helpful in that sense that when you're on landscape, those are the glue lam tables. There's several different glue lam tables. There's softwood and hardwood. That's one division. And then they're also divided by how it's used, beams versus columns. So these are members primarily used in tension and compression. Primarily, right? It's not that you can't use them otherwise. And in fact, they give you the values here, right? Don't they? Yeah, here's the bending values. So you can use it as a beam, but they're primarily intended from the layup to be a column. And we are hem fir, and I think I picked this L2. Let me see what I have. I had 13. Okay. Oh, the other thing you have to do is pay attention to how many laminations you have. Okay, axially loaded in compression, and you either have 2 or 3 lambs or 4 lambs. And in this case, we've got 6. Oh, that's what that picture had, right? I don't know if the picture's really accurate. That's just a standard picture out of here. You'd have to say, you can't tell how many lambs it has out of here, though. I think that would be under Western species, and you look up 3.5, 3.5, and we said 7. Maybe not getting that. Getting it right here. Well, I think it was it had more lambs than they should be 1.5 inches per lamb. So 1.5 inches or inch and yeah, they're 1.5 inches per lamb. So if I take the 7.5 and divide it by 1.5 inches, I'm certainly over 4, right? 4 would be 6, right? So 7.5 is 7. So I'd actually have 7 lambs. I've got 7 lambs. So 7 lambs is more. So I'm in that category. So I'm coming down this guy here, and I believe I came across with the L2, hem fur, and that's where I got this 1350. And then the other thing we used was E-min. Where's that? This is the min, axial min. So there's the times 10 to the 6. So 740,000, I guess. Okay, so those are those numbers. They come out of that table. They're also, this is a table that still has a ton of footnotes, and when we get into the glue lamb, we'll look at them in a little more detail, but there's limitations. If you only had 2 or 3 lambs, you'd have to, I think, make some sort of a reduction, right? But I think we're good for what we're doing. We don't have to worry about that. Okay, so we got the strength. In glue lamb, this is in chapter 5. We've got slightly different factors. So here we are with compression, right? We've got our D, M, T, and we still have P. V gets left off. This is the volume factor that would go into bending, but so there's no CV or CF or anything. So that one gets left off. Okay, these two are both 1. So the only, and this one we said was 1.25. Okay, so the only other one we've got is CP. We got to calculate, and that calculation is the same formula that we used for the solid lumber, dimension lumber, except for this value right here. That C is that little constant that goes in the denominator is 0.9 instead of 0.8. So here we come up then with a little bit better, right? 0.69. Huh. All right, so this is the third option. The glue lamb, and CP is 0.69. Is that one I had? Yeah, 694. Okay, so we put that on with the CD, and we come up with the allowable stress, and when we combine that with the area, which is again just slight, I think the other one was 7.25, this one's slightly larger, it comes out with 30,000. So now we've probably gotten the best one. This is P equals 30K, 3742. Okay, so that one's up to 30,000. So you've gone from 3,000, it's a factor of 10 higher, right? And it's really almost the same size. So, although of course the glue lamb is going to be considerably more expensive. It's you're paying probably, I don't think it's 10 times the cost, but it might be close. It is considerably more expensive than just a couple of pieces of dimension lumber, and might not be, I mean, in the size that you specifically want, might not be so readily available. At the lumber, it used to be they were always special ordered, but now if you go, there are some that are stocked at a lumber lot, like at Lowe's or something, and they're used for longer beams primarily, not for columns. So it would probably not be the size you'd want, but so you'd have to end up special ordering it, which would be another little bit of a thing. Okay, next option, built-up columns. Now these are very common, and what they do is they nail them together, right? And according to the specifications, the nails are supposed to go all the way through. And whether that's always done is pretty unlikely, at least like in this photograph here. Do you really think they had a nail that was that long? I mean, you could get one that long, I guess, but and then you got to drive it in without bending it. So there's probably, I don't know, but they are used as you see in this photograph for a heavier column. This would be a situation, probably residential construction, I would imagine, where you've got some heavier loads. They've even got a steel beam on top of it, but they are, trying to put it together on site, and so they've ended up nailing together these pieces. So there are some criteria for these provisions. Each lamb has to be a rectangular cross-section and at least 1.5. So you're not going to nail these together out of boards, out of 3/4-inch boards. They've got to at least be 2x or 4x maybe. Usually they're 2x, almost always. All lambs have the same depth, so this way they've all got to match their depth, okay, which would be normal. The faces are in contact, okay, yeah, that would, that seems like, I mean, most of these are pretty self-evident, unless it was super warped, it would have to be in contact. The laminations go the full length. Now that one, you can imagine some people might want to splice them together, but they should be, to meet the way that the strength is calculated in this provision, they're supposed to be full length. And the connection, which is this nailing pattern here, has to meet these specifications. I think this is probably for nails, and this might be for bolts. There are two options, nails or bolts. So, and we'll look at those in a little more detail. So here are some examples. You can see they do fit in lightweight construction. They can be pretty convenient. I mean, here meshing, they've actually left a pocket for the truss to fit into, or the beam to fit into, so that works out real well. And again, they're lightweight and you can put them together on site, so that's all kind of an advantage. Okay, so here is the procedure. Again, pretty much the same. Differences being, we've got this KF factor that comes in and gets used with CP, and the KF depends on what it's a factor for is you've got this guy here and one next to it, or several, right? And if they are buckling this way, that means the nails would go into shear. It would be curved, and the nail connection would go into shear, right? So there'd be a little bit of slippage in that connection. That's just a nail, and against the wood, it's not totally. In fact, there'd be a little bit of difference. I think there's a difference between the bolted and the nailed. Well, we can check, but in this value. So what this value is accounting for, when L2D2, L2, that's this and this way, when it's bending like this, then you've got to put this little adjustment factor in there for the nail slippage. So that would go back up on CP. Okay, other than that, it's pretty much the same. What does it say? Right, okay, yeah, and you end up, there are several slenderness ratios, and you have to, let me see, in a minute it'll show you, there are different criteria for each of them. Okay, so this gives the nailing requirements. There's a whole whole list of criteria here, and what this is simply giving you is the spacing and stuff. So adjacent nails are driven from opposite sides. Okay, so that's what they're showing here. This one and this one's coming from here, this one's coming from here. So they're supposed to be staggered from opposite sides. Nails penetrate, and this is the one that's probably not always followed, all laminations at least 3/4. So that means you've got to come all the way through, right? All the way through to within 3/4 of that, to within 1/4 of the other side of the wall. It's got to go 3/4 of the way through the last lam. So almost all the way through. You could go, I mean, if the nail were longer, you could go all the way through and then cleat the nail. That's called cleating, when you flip it and bend the nail on the other side. That would be fine. Or I think a lot of the nails are sized so that, oh, I can pass these around in fact, so that the length of them just makes it through. Like I think this makes it through, oh, I was going to say 3, maybe not 3. Okay, whatever. Maybe this makes it through 2, 10 penny. Oh yeah, that looks like it'd be exactly 2. So, you know, they're kind of sized to those lengths. Yeah, I'll tell you what, I'll pass these around. You can, I put this together, went down to the hardware store one time and got a bunch of nails just as, so you can get a sense of the different sizes. The nails are, in this country we specify them by penny. And I used to think that was by the weight. You know, there is such a thing as a penny weight. But that's not what this is. That's not the origin of the term penny. The penny is actually the cost. And this was not in the U.S. This was in the U.K., in England, probably a couple hundred years ago, or whenever they started, maybe 150 years, whenever they started making nails. The cost per, I don't know how many they sold, 100 or 10 or whatever, was that many pennies. So then that became the name of it. A 10-penny nail cost 10 pennies for whatever, 100. And then that name kind of stuck with them, and they've just used that name. There are tables, in fact, in the I don't know if I show one, but in the NDS they have size tables that give you the exact dimensions of the nails, the different ones. Okay, so, and this, right, the rest of this just specifies, you know, the end distance here has to be between, and this D here is the diameter of the nail. So D equals nail diameter. So you choose your nail, you get your D, and then based on the nail size, that's what all these dimensions are based on. Oh, here it is. D is the nail dimension. Okay, so that's kind of a lot of detail to get that. There are also, in addition to that, just nailing it, Simpson Strong Tie, of course, makes their own fasteners. And I believe these are, they say they're screws. I've not actually seen one that I've got a sample of. But they're pretty much used the same way. You know, they're supposed to be from opposite sides, but they have their own, you know, you have to go to their literature to get their specifications for it. It doesn't exactly match the NDS. That's their own. But those are also a possibility. Okay, so let's do this example. So we've got the slenderness, and here we're using LE over D2. So this is right. This one L2, the full height over this, which was the 3 inches. Right, and that comes out to be 24. So again, right about in the middle. You do have, we're back to dimension lumber, so we got the CF again. Otherwise, it's the same You know, otherwise, except for the nails, it's exactly the same as this one, right? No, I'm sorry. Same as this one, except it's the same as the first one, except it's been nailed together. Okay, so here's this KF factor, and the KF for the nailed condition, we'll use the 0.6. For bolted, it's this other one. And let's see, if it buckles this way, then it really isn't. Then you don't get that nail slippage, right? Then it would be all of the plies would be buckling together, so that would be, this is that kind of buckling. Okay. But ours was definitely, this weak axis was buckling, so we're down, we are using this one. And what else have we got? And sawn lumber. Okay, so we plug all those in to that. We got that guy. We got the Euler stress. So these should be pretty similar to what we had earlier, except we've got now a few different factors in there. So the CP comes out to be 0.2125. Okay. So this is option 4. Are we up to? Nailed. So CP equals 0.2125. 212. Okay. Exit safety right. Okay, 21. And that gives us, what do we get? Okay, so we get, put that on there, get the stress. The area is the same as what we used for the first one, but the final stress is quite a bit higher because our CP in this first one, 0.9, and here we got 2, so it's over 3 times the CP. So we come up with 7,888. All right, P 7,888. All right, pounds. So not as good as a solid, but certainly a lot better. I mean, almost double what it was in the. So this one you would certainly use over this. I mean, just for the price of a few nails, if you're trying to really make a column out of it. I mean, it's one thing at the end of a stud wall. Okay, then the strength is not critical. The doubling almost has more to do with the attachment of the siding and everything. It's not so critical there. But if you're making a column that's supporting a beam, you definitely want to have it nailed. Okay. So, and this is this is out of the NDS. These are the nailed specifications. We could just look real briefly at the last step of this thing would be to specify exactly what the nail pattern is. And, you should be following the nail pattern. So this is based on the dimension here. This is we want to penetrate 3 inches, right? So I think that's how it's coming up with a 10-penny nail. The length is 3 inches. So there's my 3-inch length. So that's full penetration then. So we got that. And then the D is, that's the one we use. So this gets used in all the dimensions we've got to figure. First one, I guess this was, I think the all nails penetrate laminations at least 3/4. Okay. Oh, 3/4 to the end would be that. But yeah, the 3-inch one goes all the way through. Then we can see some of these others. This is simply finding all these dimensions, right? So we already got that one. We got that one. The end distance here has to you have to be between these distances. So that must be 15 is 2, 2, and 18 is 2, 6. So I picked 2, 5. Okay, 2, 5 fits right between those two, right? We picked 2.5. Okay, then the next one, you've got 20D is the spacing between adjacent nails in a row. So this spacing here. So 20D, how do they do it? 20D, oh, it's between 20D and 6T min, and T min must be the thickness here. This is T min. Okay, so that is our 1.5. 6 times that is 9 inches, so we don't want to go, you can't go over 9 inches, so I just made them 8 inches. Okay, so that, and you can't have them closer, and why you'd want them closer than 2.2, but okay, so we got 8 inches, so that's where that's coming from. Then you got the spacing between rows. Okay, that must be this distance here, and that's between 10D and 20D, so between those two numbers. So I ended up picking 2.25, all right, is in between there. So you can see, you got to look at the specifications, and you've got some latitude. It's not a fixed number. You can, adjust it so it comes out to be reasonable numbers that you can measure. And the last one was edge distance. Oh, that must be this. Oops. Okay, was the also between these parameters, right? So there was the 2.25 again. We got okay, and what's the other one? 2 or more longitudinal rows. Oh, the number of longitudinal rows. Okay, so we stuck with 2 there, where D is greater than 3, and 3 was 7.25, and I think, I'm sorry, is less than, so it's less than, yeah, D is great, this is D. D is greater than that 3T min. Okay, so we went with 2 rows, which seems to work. Okay. So that, that's what all the specifications are, is just to get that nail pattern on there. Then you can also, we won't do this example, but you could do the whole thing with bolted as well. And bolted has, I think it had a little bit better K value, so, and the bolts they're talking about are probably something like this, right? There's probably a provision in there to give you the size of the bolt diameter. Here we go. You'd pick that, just like you pick the nail, and it depends. You can use carriage bolts, or you could use regular. These would probably be more commonly used, and put it together with that. Okay, so, but I'm not going to go through that whole example. The only difference is really the specification of the bolt pattern. Of course, you got different specifications, and also that K factor on the CP changes slightly, but not much. Okay. This is just the bolt. Okay. Bolt patterns and dimensions. Okay, last one, spaced columns. These are kind of interesting. And these probably are not used for columns so much as compression member in trusses. In trusses, they do come up on a big truss, potentially. And the reason, you can see, you've got members going through here anyway, right? So you've got 2 layers, and you can, space them however, but you've already got the space in there on some trusses. You could use them for a column, and maybe rarely, they probably are used occasionally, but they're a little bit more trouble to manufacture. You've got to actually route this groove. There's a groove here that this ring fits into. So this ring is kind of, oh, here you can see, they're cutting that groove. So you have to have a special little device and probably a drill press, cut the groove so that the ring fits into that groove. It goes together, and then there's a bolt that joins the two through the center. So it's a little bit more, here you see him assembling it then, like this. A little bit more trouble to put together, a little bit more trouble, certainly more trouble. You almost can't do it on site. You've got to, more likely you're going to have a drill press to do that with. I guess you could do it on site, but probably not. So not too commonly used in lightweight framing or residential kind of stuff. Okay, with these, we've got 3 different slenderness ratios we got to look at. First, the strong axis, right? There's that would be that buckling. Then you've got potentially the weak axis where the weak axis where the full axis buckles. That would be that one. And then you could also have it buckle like this, right? So there'd be 3 different buckling modes, and that's what's described by these, and there are different limits on each of them. So the 1-1, okay, that would be the big axis here. They let that go all the way up to 80, okay, higher than, the normal limit was 50. This one, 2-2, that would be, oh, excuse me, I said that wrong. That's 1, this is 2. Can I? Wait a minute. Gotta correct myself. Eraser. Get rid of that. I went to the wrong one. Okay. Oop. Wrong one again. Okay. 1, that was this one. Okay, this one. Oh, man. This one is the 80. Okay, let me just label them here. Okay, that one's the 80. This one is the normal situation we have. That would be the 50. And this one, 3-1, which would be L3, right, with 1. This one is the 40. So you've got 3 different limits. Those are the limits, right? And you've got 3 different ways that you're calculating that slenderness ratio. So in the end, you calculate all 3 of those slenderness ratios, and you'll take the highest one would control. But you just have to be careful not to exceed these limits. Okay. All right, and then we put the factors on it. This is back to dimension lumber, so we got the same dimension lumber factors. There is another factor we put on C, kind of like the other factor that we had earlier with the nail. I think it's kind of based on the end fixity, though. Depending on how thick this end bracing is, they consider that different degrees of fixity, so they adjust it with this factor there. Okay, so let's see. Here are the different slenderness ratios, and it looks like the highest one is that guy right there, the L1D1. So whichever one that was weak axis, the whole weak axis, right? That's, jeez, come on. Okay, the weak axis. This and this, okay, is what we got. Okay, and then we can calculate, let's see, you have to make some decision about the end distance to determine whether you're condition A or condition B, and that you're kind of, I think, given freedom to design that. You choose it, but it's based on either this ratio of L over 20 or L over 10. So if we look at L over 20, we've got 3.6. L over 10 would give us 7.2. So I went with the bigger end spacing, which will give us a little bit stronger. I think it gives you a better K factor, as I remember. So that then gets kind of specified. I specified that, and I could have probably said 7 inches would have been a rounder number, but I don't know. For some reason, I just did the exact number, 7.2, and then adjust the others to give me a total of 72 height. Okay, so that gets my spacing of these blocks, and the other one goes in the middle in this case. And then we get those factors, yeah, are the same as before. Here's the this adjustment factor here. You can see for the end fixity of B, it's a little bit higher, so that's the one that's the one I chose to go with. We've got those areas the same. I'm using the same lumber, and right. I just have to make sure I use the slenderness ratio that was controlling from those 3 options, and I use this K factor that matches my end fixity. And other than that, it's the same CP equation. We come out with, in this case, 0.27. So this is the 5th option, spaced, and CP is equal to 0.27. So it's, yeah, a lot better than that. A little bit better than the nailed, but not as good as, yeah, the solid or the glue lamp. So it's, at any rate, better than nailed, though, a little bit. Not a huge difference. Okay, and what else have we got? Okay, that's it. Then we calculate the stress and get the total strength. So 10,000. Okay, so in the end, what do we got? As far as the comparison, right? The winner is certainly glue lamb, and that's partially. I mean, he cheated a little bit because he was a little bit bigger dimensions, right? The cross sectional area was, as I remember, a little bit bigger, and this grade lumber was slightly more, but it was pretty close. It was only 1350, right, as opposed to 1300. So not that big a difference, but it did end up with some. I mean, it ended up with the highest strength. So glue lamb would definitely be the strongest option. And there, we could have made it quite a bit stronger. We chose deliberately kind of a middle of the road grade, right? You could have gone to a much higher grade if you wanted a better strength, and it probably wouldn't have increased the price that much. The price is, this one's a little bit more expensive. It'd be interesting to actually look up the price of all of them. I'll have to do that sometime. But I'm sure that one's more expensive, although the labor in this one is also quite a bit. So this one's also not that cheap. This one is maybe, for the strength and the cost, might be the best. I mean, it's 20 as compared to 30. It's only a third less. But it would be something you could get it easily available. It would not be special order, right? You'd go down a 4x8. You should be able to find pretty simply. This one you would never use. I mean, for a column, that would not make any sense. You'd at least use nailed together. Nailed together would double the strength. So for the price of a few nails.
Can we change the arrangement of these columns in the house for different part of the house? We can.
Oh yeah. You don't have to be consistent inside of a project. You could have both. You could have some. If you had a situation where a very heavy load was coming down, maybe you do go with glue lam, and then for something that's much lighter load, but more than a a simple stud, you could nail some together. So you can you can mix them. It's not the only disadvantage of mixing is just the confusion at the construction site. You try to simplify things for the people that are building it. Now, finally, I'll show you. I told you my son, one of my boys, is a carpenter, and he actually worked on this project, and they used these columns here are nailed. They're built up, nailed columns, and they were 3 plies thick. They're made out of 3 2x6s, and they use spruce pine fir number 2. So I was asking him, they were actually building this for themselves to use as a storage facility. And I said, well, did you have an engineer look at this? I mean, how'd you decide? Oh, no, we know how to do it. And I said, you didn't have any engineer. So they just, bought the trusses out of the catalog, and pulled everything out of tables, but did not actually. And I said, well, how about the columns? Did you? No, they should be strong enough. Okay, well, maybe we should check them, right? Okay, so I went through and I did check them. So this is the NDS, right, for the spruce pine fir number 2. They're 10 feet high, and they're let's see. Somehow I came up with a KE of 1. Let's see. I sized them for snow load, 1.15, and the LE over D is that should be the weak axis, right? That should be 3 times 1.5, right? Is 4.5. Yeah, that sounds right. Okay, so it's weak axis buckling. Came out to be 26 LE over D. So we ran through the CP. This is the CF for the nailed. And we come up with a CP of 0.218. Okay, not terrific, but I mean, compared to what we had up here, actually almost the same as the nailed example we had. I mean, it's taller, it's 10 feet high, but it's and it's 3 thick, so it came out pretty close. So there's the area for 3 of them, and then that gave you a column strength of 7,800 per column. And then if we look, I think these, as best I can tell, these are at about 6 foot on center, and the roof here, I think I had that as 18 feet. So taking a tributary area of, if this is 18 projected, okay, not the way I drew it there, but projected 18 feet by 6 feet, you come up with 108 square feet. Divide that by the total load, and you have your PSF 72, which, okay, after all, is pretty high. 72. What would they? I mean, if it's a snow load, what do we have? 25 PSF snow load in Ann Arbor. So, it looks like you make it. In fact, it's a little bit over designed, I guess, but they're certainly not in any trouble. It'd be maybe a little bit over designed, but for 3 of them. Then the other consideration is, I asked him, well, when you nailed it together, did those nails really penetrate all 3 layers? Oh, no, we didn't have nails that long. We just nailed it from one side and nailed it from the other side, and they both went through the center and maybe a little bit into the third one, but not. So I forget what he said they used, whether they used, what were we using, 10-penny nails on the, or where'd my nails go? You got my nails back here. They probably used I don't know if they really used a 16, or if they may have used a 16, and that wouldn't have gone through all 3 of them. They may have done that, and that would have only penetrated, instead of 3/4, maybe 1/4 into the third one. I bet that's what they used. and then they just had to nail. But he said, oh, well, we glue it too. So they, because that's very easy to do. They spread glue all over it and then nail them together. So he figured, okay, I guess. So the glue maybe makes up for your nails not being quite long enough, but all right. So that's the story on that. Gives you a little bit of an idea of these different column types and the different strengths and characteristics. A lot of it, of course, has to do with construction on the site. What you're, like I said, the nailed is very easy to handle on the site. You don't have to special order anything. You just have to be careful, I think, about that nail penetration maybe. But I don't know. In truth, I guess what people really do is glue it, and then they'll also, in that one that was, I had the photo of that was so thick, I'll bet you anything they built it, like they do 2 layers, and then they'd add a layer, and the nail would penetrate maybe 2 layers, and they'd add a layer, and the nail would penetrate. They'd do it like that, I would guess, which is probably not too bad, but that's not exactly what the NDS specification is. So you're a little bit on your own. I mean, that's be interesting to do some testing to see how that really compares to the NDS method with the strength of it. Probably doesn't have quite the sheer strength of the nail. If it buckles in the weak axis, having the nails not all the way through is probably not as stiff as it could be. So, oh well. All right, very good. Next week we'll take a look at. I think it's start to get into glulam in more detail. Take a look at that. Have a good weekend.